So chapter P is a chapter on fractions. A lot of times in mathematics, instead of the word fraction, we use rational. So when I look at the name of the chapter or the name of the section, it's called rational expressions. Rational means fraction. Expressions generally means problems without an equal sign. So all the problems in section 2.1 are going to be fractions without equal signs. And what the instructions preceding a group of problems tell me, ask me to do it, it's going to be hugely important, because if I just look at a generic fraction, I won't know what to do unless there's some instructions attached. And for problems 1 through 8, the instructions attached are just to substitute the given number into the expression and simplify. This whole group of problems is here to bridge between the first 8 problems and the next group of problems. The instructions just want me to take the number that's provided, change the x to that number, or whichever letter there is in the problem, and do the order of operations to simplify. And my answer is just going to be a number, and it's not going to be x equal a number, because in this case x is 0. Usually if I plug a number in for x, when I get out to y, so if I had to pick a letter for my answer, I might say y equals, but that's not really even appropriate here. Orders of operations, I need to do the multiplication in the denominator of this fraction first, and 2 times 0 is 0. I need to do the addition in the denominator of this fraction next. And my answer to problem 2 is just plain ordinary 3/5. And that's all there is to this. It's just taking the number 0, changing the x to 0, and simplifying. Problem 4 wants me to take each of the x's that are provided in the problem and change them to 4. And in the numerator, when I do that, changing the x to 4, because the x has an exponent, it's safe to put the 4 in a parentheses, but it's not necessary. I'm going to treat the fraction bar kind of like a parentheses. I kind of treat the numerator like a parentheses, the denominator like a parentheses. I'll separate them separately. The numerator, I have to do the exponent first. And then separately in the numerator, I'm going to do the subtraction of 16 minus 16. And in the denominator, the addition of 4 and 1 and get 5. And when I do this fraction, I don't want to stop here. Any fraction that has a 0 either in the numerator or the denominator, I shouldn't just say stop and not know what that fraction equals. Fractions that have 0 in the numerator are equal to 0. So my answer to question 4 in section P in section 2.1 is that fraction is equal to 0. So that's semi-important, or it's actually a big deal. Fractions with 0 in the numerator are equal to 0. When I move on to question 6, I need to change each of the b's in the numerator and each of the b's in the denominator to 6. And 3 of the 4 b's are just single b's that don't have exponents, they don't have coefficients. The 2 b's in the numerator as well as one of the 2 b's in the denominator, when I substitute, I'm not going to put that b in a parentheses. The final right denominator, I'm going to put that b in a parentheses when I do the substituting. So I'm going to make this 6 minus 2 times 6 plus 1 in the numerator. And then in the denominator, still no parentheses, 6 minus 6, and then finally a parentheses, 2 times 6 minus 5. Next, I'm going to get each fraction, or each parentheses, simplified to a single number. And what I'm writing is equal to the line above it, so I write an equal sign. When I started off writing, I didn't write an equal sign because this really isn't equal to the original problem. So first parentheses in the numerator, 6 minus 2 is 4. Second parentheses in the numerator, 6 times 1 is 7. First parentheses in the denominator, 6 times 0 is 0. Second parentheses in the denominator is really 12 minus 5, because that's 6 times 2 is 12, and 12 minus 5 is 7. I could cancel the 7s if I care to. It doesn't matter if I do or don't. If I cancel the 7s, I'd write 4 over 0. If I don't cancel the 7s, I'll multiply the 4 and 7 and get 28, 0 and 7 and get 7. My choices at this point, I could have written 4 over 0. These would both be acceptable steps in my work, but both of them wouldn't be a place to stop. If I have a fraction with a 0, I should know if that fraction equals 0 or if that fraction is undefined. And fractions with 0 in the denominator are undefined. Fractions with 0 in the numerator are 0. So my answer to problem 6 is when I plug in 6 for b, I get undefined. Last even one in this grouping, I'm going to change this x to 0. I'm going to do it with a times sign. I'm going to get 3 over 2 times 0. I'm going to do that multiplication in the denominator. I get 3 over 0, and that's undefined. The whole reason I created the first 8 problems is to help you remember that fractions that have 0 in the numerator are equal to 0. Fractions that have 0 in the denominator are undefined. That's the whole reason I wrote those sections, because the next group of problems we have to understand just that. So problems 9 through 16 ask me to find the domain of a fraction. The instructions say write the domain of the expression. An expression is a problem without an equal sign. And it says write the domain using words and in interval notation. So this is a new concept that I'll try to define it, and because I'm so cruddy at making up definitions on the fly, I typed one here. It says the domain of a rational expression or equation, the problem could have an equal sign, is a collection of values for the variable, oh my gosh, that will not result in undefined, oh my, I must have cut and pasted this from somewhere. So let me try to clean this up, because this is just obvious. I read it at one point and I liked it, but now I don't like it. So I say a number is not part of the domain of a fraction if I get undefined when I plug that number in for the letter. The algebra that we're going to need to do for these next few problems is to figure out the number or numbers that I can plug in and get undefined. And how I do that is by setting the denominator equal to 0. The only numbers that you can plug into a fraction and get undefined are the numbers that make the denominator equal to 0. So my goal now is to find the numbers that yield undefined when I plug them in to the function, or when I evaluate the function at that number. I won't say function, I'll say into the fraction. It's probably a smaller, better word here. Easy enough to do that. The algebra to do this is just to take the denominator of the fraction and set it equal to 0. So if I want to find the numbers that are not in the domain of the fraction 4 over x plus 7, the algebra first wants me to find the numbers that I can plug in and get undefined. And the only numbers I can plug in and get undefined are the numbers that make the denominator 0. I find those numbers by taking the denominator and setting it equal to 0. I claim that if I plug negative 7 in for x, if I do the fraction 4 over negative 7 plus 7, that's what I'd get if I plug negative 7 in for that x. When I put that in, I get undefined, and that's the only number I can plug in and get undefined. That's the only number that's not in the domain of the fraction. The domain of this fraction, the numbers I can put in and not get undefined, that's what the domain of a fraction is. It's the set of all the numbers that you can plug in and get something other than undefined. The only number that's not in the domain is negative 7. I should probably write this up. And again, English is not my strength, so I'd say the domain of a fraction and then I'll use a math word here, is the set of all numbers that you can plug into the fraction and not get undefined. That's what that says, but that's pretty complex. So now I'm going to answer question 10. Question 10 wants me to explain in words what the domain of this fraction is. Well, the domain of the fraction is all the numbers I can plug in that I don't get undefined, which means it's all the numbers except negative 7. It's the only number I can plug in and get undefined is negative 7. So it's every number except negative 7. And in words, because I'm asked to write the domain in words in an interval notation, for number 10, I'd say the domain is all numbers except negative 7. And we usually tack on the word real numbers. Don't want to get too heavy into theory why I say real numbers, so I'm just going to say it right now. And maybe if I feel motivated and inspired a little bit later, I'll say some more. So the domain of that fraction is all the numbers except negative 7. And that tells me that if I plug negative 7 in, I'll get undefined. But if I plug any other number in other than negative 7, I won't get undefined. That's what this means. The next thing I need to do is find the domain in interval notation. And this is a little bit easy, but maybe hard to understand. So I brought out my graphing calculator to show you graphically what this answer is relating to, because writing the domain in interval notation really relates to the graph of, in this case, 4 over x minus 7. If I want to find the domain of a fraction in interval notation, I create a number line. And number lines go from negative to positive. On the far left edge of my number line is a negative infinity. On the far right edge of my number line is positive infinity. So I create a number line that has negative infinity on the far left edge, positive infinity on the far right edge, and then any number that I'm excluding from the domain, any number that I can plug into the fraction and get undefined, goes between the infinities. And then I create parentheses, round parentheses above the breaks, a left and a right round parentheses. And in words, my domain was this. That's part of my answer to number 10. In intervals, I'm going to create intervals. The first interval in the interval notation for my domain is negative infinity to negative 7. That's just kind of shoving those numbers into those parentheses. My second interval is the interval from negative 7 to infinity. Usually when you write the domain in interval notation, you get multiple intervals, you put a U between. I can read that as union or. It says all of these numbers or all of those numbers. Any number between negative infinity and negative 7 can be plugged into the function and not get undefined. Any number bigger than negative 7 up to infinity can be plugged into the function and not get undefined. The round parentheses on either side of the negative 7, that's a symbolic way to say that if I plug negative 7 in, I'll get undefined. So those are the two answers. I broke my graphing calculator out just so I can show you, hopefully it shows up well this morning, what the graph of 4 over x plus 7 looks like and how that relates to the domain. So let me turn this on and hopefully it shows up. I'm going to put into, I got to clear a bunch of stuff here. I was doing some college algebra, obviously. I'm going to do the fraction 4 divided by parentheses x plus 7. And I'm going to sketch a graph, but I don't know what I was doing before I graphed today. So I'm going to tweak the window to make this appropriate. And that's not appropriate. So if I was to sketch a two-dimensional graph of 4 over x plus 7, what's going to happen is that at negative 7, if I count over 1, 2, 3, 4, 5, 6, 7, at negative 7, there's going to be a break in my graph. There's going to be a portion of the graph to the right of negative 7 and a portion of the graph to the left of negative 7. So the graph has two segments. The number that I can plug in and get undefined, the numbers that I can plug in and get undefined show up as breaks in the graph. So basically, this shows me that from the far left edge of the x-axis, if you know this to be the x-axis, the far left edge of the x-axis is negative infinity. From the far left edge of the x-axis up to negative 7, the graph will exist. And then the graph doesn't exist at negative 7, above x equals negative 7. Then the graph picks up after negative 7 and goes on forever to infinity. So pictorially, this is kind of the interval. The graph exists from the far left edge of the x-axis up to negative 7. The round bracket means the graph doesn't exist above a line that goes vertically through negative 7. And then after negative 7, the graph exists from just to the right of negative 7 off to the right edge of the graph. That's kind of pictorially what's happening when I'm finding the domain of a fraction. I don't need any of the theory to find the domains of a fraction. Super easy to do. So I'm going to do 12 without any theory. I'll just jump into finding the domain. To find the domain of the fraction in words, the algebra is just to set the denominator equal to 0. It's important to not set the numerator equal to 0. When I'm finding the domain in words, I ignore the numerator because the value of x that makes the numerator equal to 0, in this case 3, doesn't provide a break in the graph and it doesn't make the function undefined. The only algebra I do is set the denominator equal to 0. So in this case, the denominator is x minus 4. I'm going to set that denominator equal to 0 by adding 4 to both sides. That's the only number that I can plug into the function and get undefined. So it's the only number that's not in the domain. To write the words, I'm going to use the sentence, the domain is all real numbers except. Every time I go to write the domain in words, I'm going to use those same words when I'm finding the domain of a fraction. The domain is all real numbers except, and then I'll tack on the work that I just did. In this case, it's going to be except x equal to 4. This is the domain written in words. I don't need a graph. I don't really need to know any theory. I can find the answer to the domain without doing any algebra. or without knowing much theory, I need algebra. To do the domain in interval notation, which is next thing that's asked, I'm going to create a number line, put negative infinity on the far left edge, positive infinity on the far right edge, any number that I'm excluding from the domain between the infinities, and then I start making round parentheses. The first interval that I'm implying goes from negative infinity to positive 4. Round parentheses tells me there's a break, and I exclude that number. Square brackets would include that number. Second interval is going to be 4 to infinity. And I'll put this union symbol between. And that's the answer for the domain in interval notation. Let me sketch a graph of this just so you can, for those of you that are visual, I'm going to sketch a graph of y equals, I think I can do fractions on this. I forgot how to do it. Math? Fraction, is it? No, that's no good. There's a way to do fractions. Was it alpha y equals? Yeah, alpha y equals, I can do fraction. So my fraction is going to be x minus 3 over x minus 4 that I'm about to graph. You don't need to graph this, but for those of you that are visual, I like to show this if I can. Setting up my window just to make this nicer. The graph is going to look as such. It's going to have a break at 4. Right here, there's a break at 4, and it crosses the x-axis at x equal to 3. There's not a break at 3, but there's an important feature of the graph at 3. So real quickly, for those of you that are visual, the graph of this looks something like this. It has two halves, a left half and a right half. The only place where the graph has a break, where the graph has breaks, those are numbers that aren't in the domain. So the value that made the denominator equal to 0 produces a break at 4. The value that makes the numerator equal to 0, it's an important feature of the graph, but it's not a break. It's where the graph crosses the x-axis. So for the domain here, I'm going to go to define the portions of the graph. The first portion of the graph goes from the far left of the edge of the x-axis, which is at negative infinity, passes through the x-intercept, and there's physically a break at above x equal to 4. There's no graph above or below x equal to 4. The second half of the graph picks up after the break, and it goes on to the far right edge of the x-axis, and the far right edge of the x-axis goes to infinity. That's visually what's happening for my domain. We don't have to do the domain with looking at graphs. It's only algebra, and the algebra is really minimal. To find the domain of any fraction, the algebra is exactly the same. Whether I'm doing the domain in words or the domain in interval notation, the algebra is going to be the same 100% of the time. The algebra to find the domain of a fraction, and that's what I'm doing for problems 14 and 16, is to ignore the numerator. The numerator doesn't impact the domain because the only way a fraction can be 0, or undefined should I say, is when the denominator is 0. So anytime I'm asked to find the domain of a fraction, I ignore the numerator. The algebra is to solve the denominator equal to 0, and that's going to give me the number or numbers needed for the words and for the number line part of my domain. So algebraically for number 14, when I go to find the domain, I'm going to set the y squared minus 6y minus 7 equal to 0, and I'm going to factor this. I still have this guy around. This is a minus minus, so I knew I need plus minus factors, small number plus. So when I go to factor this, I'm looking for numbers that multiply to negative 7, that add, that's really subtracting, to negative 6. It's going to be the numbers for my sight factoring are going to be 1 and negative 7, because 1 times negative 7 is negative 7, and 1 plus negative 7 is the same as 1 minus 7, which is negative 6. So I'm going to cite factor, create two parentheses. I don't need grouping because there's not a number in front of the y squared. The lead coefficient is 1. In my parentheses, I'm going to put a positive 1 and a negative 7. The numbers that are going to go in my answers are going to be negative 1 and positive 7, because when I set the y plus 1 equal to 0 and isolate the y, you get negative 1. When you set the y minus 7 equal to 0, you get y equal to 7. Now I'm ready to write my domain in words. That's easy. I'll say the domain in words is all real numbers. Maybe I'll abbreviate numbers with a symbol, except y equal negative 1 and 7, because my letters are y. To do intervals, it's a little more complicated, but it's not so bad. The interval domain, I create a number line that has negative infinity on the far left edge, positive infinity on the far right edge, and then in a proper order, the two numbers I'm excluding from the domain. And I'm going to create parentheses that imply the intervals here. I'm going to get a left parentheses, a middle parentheses, and a right parentheses. And I'm going to load those up with numbers. So my domain in interval is going to be the interval from negative infinity to negative 1, which means any number between negative infinity and negative 1, you can plug it in to the function and not get undefined, but you can't plug negative 1 in. And then negative 1 to 7, double round parentheses, which means I can't plug negative 1 or 7 in. If I plug those in, I'll get undefined. But if I plug anything between those in, I'll get something other than undefined. And then 7 to infinity. I didn't leave myself enough room, so that third interval, it should probably all be written on one line, but I just ran out of room. So those are the two answers for 14. And the graph is useful, but it's hard to get a good window on that graph, so I'll kind of punt on graphing that. 16, same structure. I'm asked to find the domain of a fraction. That's the only time I do the algebra of ignoring the numerator, solving the denominator equal to 0. In general, if I'm presented with a fraction, I would never just randomly do this algebra of ignoring the numerator and setting the denominator equal to 0. I only do this when I'm asked to find the domain. So for problem 16, I'm going to ignore the numerator. If you set the numerator equal to 0, graphically, the answers to it are going to be where the graph crosses the x-axis. And that has nothing to do with the breaks in the graph. I'm going to set the denominator equal to 0. Because the denominator doesn't have a number in front of the squared, I'm going to cite factor. It's double plus. The numbers that I'm going to fill into my parentheses need to multiply to that last number 20. They need to add to the middle number 9. And that's just going to be 5 and 4, because 5 times 4 is 20 and 5 plus 4 is 9. Now that I have it factored, I can split the parentheses up and get the answers that are implied when I set those factors equal to 0. The b plus 5 factor, I'd minus 5 from both sides. You should do that in your head and not show this algebra. And the b plus 4 factor is going to give you a b equal to minus 4. So in words, I'm going to use the same words. I'm going to say the domain is all real numbers except b equal to negative 5 and b equal to negative 4. For intervals, I'm going to create my number line that has negative infinity on the far left edge, positive infinity on the far right edge, and then in the proper order, get the negative 5 and the negative 4 on that number line. The negative 5 is going to be further left. As you go left, in some sense, the numbers get bigger when they're negative. I'm going to create my intervals. I always get one more interval than numbers other than infinity that I put on the number line. So here, my interval domain is going to be negative infinity to negative 5, double round bracket, negative 5 to negative 4 as an interval, double round parentheses, union negative 4 to infinity, double round parentheses. That's everything for domain. I always put a question for domain on the test, but this is kind of one of these things that's not like the other. As we go through the chapter, the domain questions won't come up again, and it's easy to forget about this. They're not particularly hard to do, but they're easy to forget because it doesn't fit in with the rest of the chapter. We won't do domain again for the rest of the chapter. So I'll pause. We'll probably have a part 2 and 3 for this video.